The topic of this video is unitary operator and the transformations involving unitary operators. An operator U is called unitary if U dagger of it is equals to U inverse of it. That means if we compute the Hermitian conjugate of the operator U, you should be getting the inverse of U. For the case of matrices, U dagger is also equal to U star and then transpose of that. The transformations of state functions or operators involving unitary operators are called unitary transformations. And now we see how we can have the transformed state functions. Let us take ket psi and ket phi as two wave functions of a system. If the unitary operator U acts on these kets, the new ket states can be psi prime and it's equal to U acting on psi, and then phi prime is equals to U acting on phi, and let us call these two as equations number 1 and 2. So these we can say the unitary transformations for state functions. And now we try to understand how the operators will be transformed by the action of unitary operators. Let us take a linear operator A such that if it acts on psi, it will be giving you phi as equation number 3. We knew that when U acted on psi and phi, it transformed them into psi prime and phi prime. And let us say that equation number 3 is also transformed to this equation where A prime is acting on psi prime and giving you phi prime, similar to the equation number 3. Then by using the equations number 1 and 2, in place of psi prime you can write U psi, and in place of phi prime you can write U phi. And from equation number 3, the left hand side we had phi, so in place of phi here we're writing A psi. So now we can actually see that A U acting on psi is giving you U A acting on psi. Of course here we had A prime U acting on this is giving you U A. So we can actually say that A prime U is equals to U A, and we can call this as equation number 4. And now if you multiply this equation number 4 by U dagger from right side on both sides, we see that A prime U dagger is equals to U A U dagger. And by the property of unitary operators, U dagger is also equal to U inverse, and that's equal to identity operator I. That is, since U dagger is equal to U inverse and U inverse is equal to I, we can actually get A prime is equals to U A U dagger. And if we had multiplied equation number 4 by U dagger from left side, we should have been getting A is equals to U dagger A prime and U. So we can say that under the unitary transformation, the operator A has transformed to A prime operator, which you can obtain by this product. And now we try to understand what kind of form for the unitary operator we can give, so that if it can transform a basis set into a new basis set. Let us say that we had this old basis set which is complete and orthonormal, uh, which we are writing as KTAIs, and it is actually kind of transformed to a new basis set, uh, uh, which is again complete and orthonormal, uh, but this time they are denoted by this ket BIs, and then that can be achieved by unitary operator, which is u, and it's given by summation over k and ket bk and bra ak. And we'll try to check this thing by performing mathematics. I mean mathematical calculations. So if u acts on AI, ket AI, we can write in place of u the summation that we had here. And then when we write these AK and AI together, uh, we see, we see that the scalar product is equals to 1 if we had k is equals to I, and then it is equals to 0 if k is not equal to 0. And the same thing we can also say as our Kronecker delta function delta ki, which is equals to 1 only when k is equals to I, and it is equals to 0 when k is not equal to I. So in place of this scalar product, we are writing our delta ki, and we are writing this ket bk as it is. And when the summation is done, we'll get the answer as ket bi. So we are seeing that this ket ai is transforming into ket bi by the operation of u, which is of this form. Check number 2 is for u dagger into u, and u was defined like this here, and if you take its dagger by the property of matrices B and C, if you have their product BC, and if dagger is taken on top of them, then we'll be taking the daggers for them but in a reverse way, C dagger and B dagger. And for the dagger of a bra vector is its ket, and then the dagger of a ket is bra. So we should be getting this for u dagger. And if we have taken u with the summation index L, then when we write the summations before, and then when we had AK and this BK and BL written together, it will become a scalar product of BK and BL, and AL comes as it is. And in the next step, for this scalar product, we can actually substitute this Kronecker delta function for KL, and this says that only when k is equals to L, we'll be having 1, and then it is 0 otherwise. So the summation over L will give you here AL, I mean AL is equal to AK. And then from completeness relationship, this summation also is equals to identity operator I. Therefore we can say that the operator u, which we have taken like the summation here, is actually transforming your basis set ai into another basis set bi. That's it in this video. Thanks for watching.